Okay, so what I'm going to go through is this graphing motion activity. And what we need to think about is we're thinking about a projectile that starts with an initial y velocity of 0 meters per second. And it has an initial x velocity of 5 meters per second. Okay. So remember, we're thinking about projectile motion. So breaking it into our y and x components are extremely crucial, and understanding what's happening in projectile motion is also crucial. Key thing, remember, with our horizontal motion is that there are no forces in the x direction. So our Vx is constant, okay? So that's crucial. So we're graphing distance here over a certain period of time. So if it's moving at 5 meters per second, what that means is every second it's moving 5 meters. So it starts at 0, so this is 0. And then after a second, it's moved 5 meters because it's moving 5 meters every second. So 1, 2, 3, 4, 5. We have 5 meters in 1 second. This is 15 meters in 3 seconds, and so on. We're going to go all the way up to 6 seconds. Okay, so that's the x. Every second it moves 5 meters because we have a constant velocity. It's not as easy for the y, because what's happening for our y is we have acceleration due to gravity, or the force of gravity acting on our object. And if we remember, the gravitational acceleration is equal to 10 meters per second squared. What this means is we increase the speed of our object by 10 meters per second each second. So that means that its speed is increasing as it's moving down. Okay, we're increasing the speed by 10 meters per second each second. What that means is we need to use one of our equations to help us find that vertical distance that it's traveling. So how do I find the vertical distance? What I can do is I can use my equation delta y equals the initial speed in the y direction times the time plus 1/2 my gravitational acceleration t squared. Well, what we know is our initial speed in the y direction is 0. So that cuts out this part of the equation. And I can use delta y equals 1/2 gt squared to find the y distance for each moment in time. If we had an initial y speed, we could also use this to find the y distance at each moment in time as well. But since it's 0, it makes it easier. So for example, at 1 second, we plug in delta y equals 1/2 10 meters per second squared times 1 squared. So delta y equals 5 meters at 1 second. At 2 seconds, same thing. Delta y equals 1/2 times 10 times 2 seconds squared, and you get delta y equals 20 meters if you plug that into a calculator or solve that in your head. Okay, so then we go to graph this, and it's helpful. You can label these 10. I just go every other line, so they're 5 apart, or 5 meters each line. So 10, 20, 30, 40, and so on. And we can graph this at 1 second, it's at 5 meters. At 2 seconds, it's at 20 meters, and so on. And then we can use that to help us draw the projectile motion, okay? We combine our x and y, so at 1 second we were at 5 meters in the y and 5 meters in the x direction, so that's going to be my point right there. At 2 seconds, we were at 20 meters and 10 meters in the x direction, so that's my point. And you'll continue down, and you're going to see that it follows this curved path that as time goes on, our y continues to get a farther and farther distance apart due to this acceleration, where our x stays the same distance apart because it's a constant velocity. And so you'll finish this out up to the 6 seconds, and you're going to see that it's going to be a curved path that comes down that follows the projectile motion. So you'll want to find delta y for 1 through 6 seconds, graph it on the y-axis, and then use those points to find your projectile motion there.